Let's begin chapter 11. This is a chapter on drag and lift, a classic problem in fluid dynamics. And this is a look at the roadmap and the learning objectives for this chapter. So previous chapters have described the hydrostatic force on a panel, if you remember this way back. And also we've looked at the buoyant force on a submerged object and also the shear force on a flat plate that we saw in chapter 9. This chapter is going to expand this by looking at lift and drag forces. And the classic problem here is on airfoils or hydrofoils. Please note that we're only going to consider the first three sections, and this particular video is on the first section, 11.1. So, some definitions. The drag force is the component of the resulting force that is parallel to the free stream velocity. So if you look at the figure here in the bottom, they're using the example of a kite here. And you can see the kite is, the free stream velocity is kind of coming from the left to the right here, and it's elevating the kite. So if you idealize the kite here as just a straight line here, the kite is angled into the wind, into the free stream velocity. And we can see then that the drag force is going to be the component of the force that's parallel to the free stream, and the lift force is going to be that which is perpendicular. And of course, the lift force is the force that drives the kite vertically. And so we have the definition here: the lift force is the component that's perpendicular to the free stream. So pretty easy to understand. We're just separating this. The resulting force into the two components in the direction of the free stream and perpendicular to the free stream velocity. When we look at a more complicated situation like an airfoil, we know that there's a pressure distribution that forms on an airfoil, which allows, for instance, an airplane to fly, and that is given by these this distribution here. This is just an approximation of that, and in fact we can see that there's a positive gauge pressure on the underside of the wing, as well as a negative gauge pressure, or what we call a vacuum pressure, on top of the wing. And since there's a positive force upward, this is going to give lift to this airfoil, which is the principle upon which aircraft work. In addition to the pressure force always being perpendicular to the airfoil, at any point along the airfoil, the pressure is perpendicular, just as we saw when we were working with controlled volumes. We see, in addition to that, we see a shear force that is being enacted along the or tangential to the surface. So if we now look at just a little piece of that surface here, if we expand this little piece out, we can see that there's going to be a pressure force and there's going to be a tangential force. And so the entire pressure force is going to be the pressure times the little element of area that we're considering, and that's going to be in this direction. But we're going to be able to pull that out into a horizontal and a vertical component. Note that implicitly not shown here is some sort of Cartesian coordinate system, maybe x and y, where the drag force is going to be in the x direction, and the lift force is going to be in the y direction. And the free stream velocity is actually in that same x direction. But since the pressure distribution is, or the pressure force is not vertically aligned, but instead is aligned perpendicular to the surface, then we have an angle, and we're able to express the pressure force into its horizontal component and its vertical component. The same thing can be done for the tangential force along the surface. Again, that surface is inclined with respect to, say, the x-axis, and so we have a horizontal component and we have a vertical component. So to look at the balance of these forces, to look at the the drag force, for instance, we're just going to add up this value and this value, and to get the lift force, we're going to add up this value to this, to this value here. And so we're just going to sum up the horizontal components and the vertical components. And that's exactly what we do. So for the lift force, you can see that this is minus p sine theta, and it's going to be minus tau cosine theta, both of those times dA, which is what we have here, both minus signs. And in this case, in the horizontal case for the drag force, Fd is going to just be the addition of this plus this force here, which is exactly what we see. So that kind of defines how we would determine the lift and drag forces over a particular foil. And in fact, to determine the entire forces, you would have to integrate over the surface area basically over the area of the entire airfoil to get the total forces. And so, but that's possible if we know the pressure distribution and the shear stress across the surface. Now, one other definition that we have for this section is just to define the drag force as in terms of both the form drag and the friction drag. So the drag force, the entire drag force, is going to be equal to the form drag, which is basically the pressure component of the drag, plus the friction drag, which is going to be due to the shear stress. And of course, the total drag force then is equal to the form drag plus the friction drag. And these are just convenient definitions that are used when we talk about lift and drag. So that's it for this particular section, I believe. Yes, and stay tuned for section 11.2 next. Thank you.